again, well, for the kind introduction. So it's a pleasure to be back in Cape Town. So we had a really nice discussion last time. So please go ahead and ask questions at any moment. The goal of the talk is not to reach to the end, I think, but yeah, but I'll try. I usually never end, never get to the end. Well, that's good. So the outline of my talk is this time is of course much more focused. So having this nice opportunity to talk to you last time about kind of general ideas and heavy ions in general, we now focus on kind of the stuff that we've been working on here in our group in Bergen, and that's more related to how jets lose energy in quark-gluon plasma, as we said. So we'll talk first about how partons propagate through the medium, how they how they interact with the medium such that you get induced radiation. So basically bremsstrahlung. And the second part of my talk, I'll try to discuss how to go from this picture of a single parton that radiates to kind of to the picture of a whole jet losing energy. So a single parton that will radiate a gluon, and that parton will have slightly less energy. And the same happens to a jet. It basically loses energy as it goes through the quark-gluon plasma, and it will ultimately end up in a different energy. And then the main kind of application of this is to compute the so-called nuclear modification factor, RAA, which is the ratio of basically yields of jets in heavy ions versus PP. And if I have time, I have one slide on kind of how you would start thinking about substructure observables, so basically how the jet looks like inside. All right, so just starting out from a generic kind of motivation is to say that we have hard probes that are we are most interested in hard probes, which are processes which take place on short timescales and involve much higher energies than what governs the development of the whole quark-gluon plasma. The scale of the quark-gluon plasma, the energy scale is obviously related to the temperature of the quark-gluon plasma or its kind of local energy density. While when we are talking about hard probes, we're talking about which is the temperature of the quark-gluon plasma is of the order of a few hundred MeVs, perhaps, as high as that. But when we're talking about jets or heavy quarks, we're talking about a factor 10 bigger for heavy quarks, perhaps a couple of 5 GeVs for the bottom, and then for jets we go all the way up to a TeV scale. So obviously those jets, in order to have this kind of energy, were created in a hard collision and a 2-to-2 perturbative QCD collision. And although there is no kind of factorization theorem proven for heavy ion collisions in the presence of final state interactions and whatnot, one can somehow, just from looking at the scales, from these kind of comparing the temperature of the medium to typical jet energy, you somehow still have this kind of separation of scales, in the sense that you will have a short range, short distance hard physics producing the jet. Now you'll have some intermediate distance physics that exactly involves the interface between the jet and the medium. And then ultimately you have this very long distance regime, which again is dominated by non-perturbative hadronization effects, which are which should be again kind of vacuum-like. But of course, now we're thinking about very, very separated energy scales. But of course, if you're thinking about low PT particles, right? By low PT I mean tens of GeVs, which is not so small, right? But of course, these kind of very idealized picture could be mixed, and it will create some additional problems. But in principle, the picture that I'm going to kind of have in back of my mind is this picture here, where we kind of have this nice separation between the scales. And so again, what we will be interested in is exactly thinking about this intermediate stage, what happens here in this, when the jet or the parton builds up to become a jet and as it propagates through the quark-gluon plasma. So this picture we had before and last week, it's basically the kind of visual visual manifestation of jet quenching in the CMS detector, where we, from a heavy ion collision, you create roughly tens of thousands of particles. However, you can clearly make out, which creates you kind of a background of dense of particle production, of energy deposition all around in your detector, but you can clearly make out a clear jet on one side, a clear excess of energy deposition in one side, while on the other side you see that the back-to-back jet, which leading order perturbative QCD should give you simply energy conservation, energy momentum conservation. You see that it has been quenched, it has lost a significant amount of energy. So so this is the setting the stage for our exploration here today. So let's start with the first part of my talk, which is the parton propagation and how while propagating in the medium, a parton would then be tempted to start radiating or losing energy this way. So what we're typically thinking about when discussing this problem is a certain frame. We're discussing typically this in a certain frame in the back of our mind. So the thing we have in the back of our mind is basically a probe that is boosted at a high energy probe that kind of moves in the positive z direction here, right? And forward in time in this space-time diagram over here. So this direction of this light cone, we will call that with this light cone variable x plus. So in principle, a high energy particle, massless high energy particle, for instance, a gluon or whatever this is, it's moving almost with the speed of light in the z direction. It will basically be moving along the x plus light cone. And in the opposite direction, you have the medium. So the medium is boosted somehow in the opposite direction, in the x minus direction, basically. So in principle, this background field, and this is what we're going to discuss now. So how does this blue particle, this our probe, propagate through this green area here, which somehow signifies the extent of the medium. So or source of density where there is some background field A0. So first of all, we can simply choose a gauge, which is a so-called light cone gauge, where we simply say that the plus component of this background field A nu is 0. We have the freedom to do that. So that's going to be our gauge choice, and then in that case, kind of the momentum of this particle here, the blue particle, the biggest component of that momentum will be P plus, and that will couple directly to the A minus field. A second thing that so what happens is basically as we go through this field, we have this kind of Dyson-Schwinger kind of resummation of multiple scatterings. So what we have here is G scalar is just basically the final propagator, or basically G0 is the final propagator. So it's basically just I over P squared in momentum space. And here we're just looking at this propagator in coordinate space. It's just a Fourier transform of the final propagator, let's say. However, on top of this, so as you can see, there's a difference between G0 and G scalar. So by scalar, I mean that I now have stripped away all additional factors related to the spin of the quarks or the polarization of the gluons and stuff like that. So on top of the scalar propagator, there will be projectors which will tell me whether this is a quark or a gluon or just a scalar particle. And what remains here, as you can see here, what remains here is exactly kind of a Dyson-Schwinger equation, which resums multiple interactions with the medium. So as you go forward in time here, you can scatter one or several times on this, in fact, arbitrary many number of times with the background potential. So the vertex of this interaction is just P plus times A, which is A minus basically. So I write this calligraphic A here because if it's a gluon, it has a different color representation. If it is a quark, it has a different color representation, etc. Now, the thing that really makes this problem simplified is again taking the P plus to infinity limit, basically. And that tells me that, so the extent of the medium is, of course, it's extended in the x plus direction. So that's what I call the length of the medium. It's basically this extent. The particle enters the medium here and exits the medium over there. But it's extended x minus, or the extent that my particle will see the kind of structure of the medium in the x minus direction is related by the Heisenberg uncertainty principle to 1 over P plus. So when I take 1 over P plus to 0 or P plus to infinity, basically my wavelength in the x minus direction diminishes to basically 0, and I'm not sensitive at all to the medium in the x minus direction. So in other words, the medium will have basically a longitudinal coordinate and a transverse position, but the x minus, the fourth direction, will be, I can completely neglect that. And this is what's kind of embedded in this equation. And then, in fact, what I end up with is, so I end up with basically my longitudinal momentum is conserved. So there is no way my longitudinal momentum talks to the medium. In this sense, my particle just flies through the medium without losing energy. And this is basically leading me to another propagator, which I call calligraphic G. But don't worry about that. The calligraphic G simply means that it's exactly just it's just a scalar propagator where the plus momentum is conserved. And what happens to the particle then, as it goes through the medium, is described by this this equation down here, which is in fact is a 2 plus 1 dimensional or 2-dimensional time-dependent Schrodinger equation. And the funny thing is, so this is kind of an example from well-known, basically from light cone kind of perturbation theory, or light cone, this kind of light cone physics, that are dynamics basically reduced to the Schrodinger equation instead of, let's say, the RHIC or something like that for quarks, right? So we see here that the way this particle behaves, the propagator of this particle simply.
Hi, Konrad. There's a question.
Yeah, I'm sorry.
Hi. So when the parton actually goes through this medium, does it describe some sort of scattering process, or I'm just because in the CGC formalism we have a similar setup with the background field and a parton passing through the background field, and I'm just wondering to what extent is that similarity extended, so to speak.
Very, very similar, yeah. So if you can see here, what I have included in the Schrodinger equation, so exactly, I mean, it's very, very similar to a typical CGC kind of setup that you refer to, but what I have here is a term which describes transverse momentum, modifications, or not transverse momentum, sorry, movement in the transverse space. So you see here this is kind of a 2-dimensional random walk in the transverse space here. And the funny thing is that the mass that would typically sit in the Schrodinger equation is the energy. So what happens in the CGC typically, you would say that this energy is so large that you basically drop this term. And in that sense, you just basically have to exponentiate the potential, and that gives you this path-ordered exponential, which is the Wilson line. Right, so a typical propagator in the CGC would have a fixed position in the transverse plane, and along that position you will resum multiple scatterings, which is this term here, which will just give you exponentiation, which will give you just a Wilson line. The additional ingredient here is that in addition to this Wilson line, we basically have the possibility of diffusion in the transverse space. That's the difference.
Okay, thank you.
Yeah.
Well, let me actually follow up. I think that's a really great question, and the reason I'm following up is because you explained it so well. So when do you think it's safe, for example, in the CGC context, to neglect in this middle term, or maybe a different way to phrase it is, why in the jet quenching context we cannot neglect that term?
Right. So in the CGC context, typically you would have a initial electron, which is very energetic, and it will radiate a photon, which will split into a quark antiquark pair in the end. But anyway, the probe that probes your medium is extremely highly energetic, right? It's basically accelerated in the accelerator. So typically you have a quark antiquark, right? The photon will split into quark antiquark pair, and those two guys will go through your medium, and those are definitely very high energy objects. However, in the what you could be worried about is are perhaps soft gluons that will be radiated of these two of this quark antiquark pair. Those guys will basically be inheriting the energy, but they will also be emitted at small x, so they will inherit just x times that energy. And the higher kind of order fluctuations perhaps will be sensitive to broadening in the medium, right? Because in the beginning they will basically inherit the energy of the electron and the photon, etc. But after a while their energy will be degraded. So you could maybe think about that those guys will be could experience some broadening. On the other hand, this broadening, as we will see, is of course also enhanced by the length. So if you have a small system, then in any case you will not pick up much, right? So there's like a balance. In the heavy ion context, you have a large medium, and we are also looking at much softer probes. Yeah.
Well, just to push a little bit further. So at the EIC that's going to be built, I would imagine that the P plus is same order as the jets at LHC. If you have a 100 GeV jet at LHC, the 100 GeV nucleon and then the few GeV electron, the P plus should be about the same at the EIC. And then one should again see a length enhancement, right?
Yes, definitely. So, and people have been speculating also that these kind of terms would generate use also some kind of initial anisotropy. So there it's basically Tolga. I don't know. You probably know Tolga well, but Tolga Altinoluk. He's been pushing this kind of program of next to iconal, what he calls next to iconal expansion. So it will be basically trying to build in this guy here, order by order somehow.
That's interesting. I'll get the name off you at the by email. But let me say one last thing, which is to push back on the energy loss side. So if I look at your diagram, it seems like the P plus of the jet is so large that you're free to boost out of the lab frame and into a frame in which the medium itself is moving on the light cone in the opposite direction to the jet. So that does seem like even in the jet quenching picture, this P plus is huge, right?
Yeah. So you could always go to this frame. Now the question is whether one over P plus makes you so the real bonus of this frame is that in this large P limit you basically reduce the dimension of the system basically. Yeah. So if you for a completely general equation like this, you would have to include also longitudinal momentum exchange. So you would be basically degrading P plus as you go, which wouldn't lead you to a nice 2+1 Schrodinger. It would give you a much more ugly thing. So, but yeah, that's something very interesting, yeah, to look at, for instance.
All right, super. Thank you very much.
No problem. Yeah, thanks for the question. So, yeah, great. So what we have is this funny picture where in the high energy limit you basically have a parton going through the medium, and at each step in X plus, so basically at each time step and at the same time in Z, at each light cone time, you have a sort of a random walk in a plane perpendicular to that direction. And yeah, probably won't go so much into the details here, but it's just to say that we also assume that the medium is kind of tractable using perturbative techniques, in the sense that when we interact with some medium object, right, we exchange some momentum, which is of the order of the screening mass of that thing. So it's roughly the Debye mass. And so the extent of that potential, kind of the extent of the time it takes to interact with that particle is roughly 1 over the momentum that is being exchanged. And that typically we assume that is much smaller than the typical the distance between different scattering centers. So we assume that the mean free path is larger than the inverse Debye mass. And finally, the length takes care of the largest scale of the problem, right? So that's basically, you can broaden from the beginning of the medium to the end. And those kind of expectations are realized in the so-called weakly coupled limit of a thermal QCD medium, where parametrically you would have that the Debye mass goes like GT, while the inverse, while the mean free path goes roughly like 1 over G squared. So it's exactly this. For small g, you would have this strong separation. So that's kind of, if I wouldn't have this, I would have to go and join your course as well and learn about ADS. But typically we assume that this is the case. We can do kind of a perturbation analysis of this. Yeah. All right. So now just a quick recap about what happens in the vacuum. In the vacuum, you don't have all these interactions. And in the end, what we'll be interested in is mostly this particle splitting, right? So in the vacuum, we typically have that because this initial particle here is off shell by some amount, it has the possibility to split into 2 particles at the end, right? Which we assume are nearly on shell, at least compared to this guy. And in that case, this gives us this famous soft and collinear divergent spectrum, which tells us that the probability of splitting this particle A into particles B and C is proportional basically to the alpha S, of course, the color factor of this guy in the beginning, and then basically it has a divergence at small angles, and it has a divergence at small momentum fraction z, or small energy of this guy, which basically tells you that in that limit, this parton here becomes on shell, in fact. But it tells you simply that if you have a hard particle, if you have a very energetic particle close in angle to that particle, you can always resolve an additional gluon or an additional quantum, because it's clearly divergent, on this level. But what you should do then is to ask yourself, well, I spent alpha S on just radiating this additional gluon. That sounds like a bad deal, right? I'm suppressed if I look at a fixed order expansion. This process here will give me kind of a next to leading order correction to my whatever I'm studying. But the point is that if I look, for instance, for all possible gluons that can be emitted within a cone, right, with transverse momentum down to, let's say, some infrared scale lambda QCD, then I see that the probability, if I take the integral of the whole phase space, then this alpha S is going to be compensated by a log square of this phase space. So typically by the initial energy here, which I call PT, right, and this cone, so there's a jet scale called PT times R, and the ratio is versus this non-perturbative scale lambda QCD, and then there's a log square of that. So if this log square is compensating alpha S, then I have a big probability for an emission to happen or for multiple emissions to happen. So I need to do resummation, which is basically the DigiLab evolution equations give me exactly this process here, iterating multiple gluon emissions according to this splitting probability. Now, what happens in the medium is very interesting, and I can use kind of arguments from a typical vacuum emission, which I saw in the previous slide, to kind of estimate and guess what will be the feature of the spectrum. So if I have 1 to 2 splitting in the medium, I have to take into account that all my partons will will experience momentum diffusion, right? Momentum broadening. So they, in other words, they will acquire a transverse momentum, which is of the order of q hat times the time, some time, right? Either if you have a parton that goes from beginning to the end of the medium, then the time would be L, so the length of the medium. For this particular case, you would say that the typical time you should put in here is exactly this formation time, or the time it takes for one parton to become two, right? So you have here, this is the concept of a formation time, which is quantum mechanically related again to kind of the uncertainty in resolving one or two particles. And it's given by this estimate here, omega over k perp squared, where omega is the energy of this emitted guy. And if I just assume that this initial guy here is almost on shell, right, then all the transverse momentum I accumulate is given by the diffusion from the medium of this gluon. Then I basically get this nice estimate. I just have to solve for formation time in this equation here, and I get this estimate here, that it's proportional to omega, or square root of omega. And this is some kind of a interference effect between multiple interactions here. And it's called the Landau-Poramachuk-Migdal suppression or interference effect. The most important thing is that now I screened my collinear divergence, right? I have interacted with the medium, so I have exchanged some momentum with the medium, and therefore there's no collinear divergence as I had in the vacuum case. And from that I can estimate my spectrum much more simpler. So if I would have kind of incoherent scatterings of these objects, then I would basically say that per mean free path along the length of the medium, I radiate a gluon. So I get omega, the omega factor, like in the vacuum, times alpha s in the color factor, which is exactly the same as here, right? So dz over z is basically the omega over omega. However, now due to this interference effect, what I have to replace the mean free path by formation time. So basically, by all these scatterings here within a formation time act as kind of one effective scattering center. This is kind of the qualitative typical picture that we have about medium radiation. Now the picture is actually extremely interesting. So parton splitting in this context is very interesting. And again, what you would use here are techniques from kind of light cone perturbation theory or something like that. In the end, what I wrote here is basically a parton splitting in the amplitude, and downstairs a parton splitting in the complex conjugate amplitude. And I can define my time axis in such a way that basically I just place the two diagrams under each other instead of having them kind of next to each other, just rotating the one under the other. And I see here that kind of from time 0 to time one, I have kind of two particles going through the medium. Between time T2 and T1, I have three particles in the medium, and from T2 up to L, let's say, I have four particles. And this is exactly what you get. In the end, your calculation of this full splitting process 1 to 2 involves two body correlators like this, a three body correlator in the middle here, which describes the kind of what happens between splitting, which some you could call it also a kind of like a formation time. And you have also four body correlators, which have their own interesting structure. So the problem of parton splitting in this picture is very interesting, especially since all of these lines can fluctuate, right? They're not straight line trajectories necessarily, but they're fluctuating in the medium. So coming back to this to our spectrum that we're actually looking for, the emission spectrum, then what's most important is this three body correlator here, which basically, this line in the middle and the upper line are the particles in the amplitude that have already split, and the guy underneath here is the particle from the complex conjugate amplitude that didn't split yet. So in the end, what I have here, after I've taking medium averages, as I didn't mention in the previous slide, but all of these correlators should be averaged over medium configurations. So after taking such an average over medium configurations, very similar to the CGC kind of procedure, I would end up exactly not with correlators just of Wilson lines, but I end up with this kind of correlator with an additional kind of kinetic term. So this really tells me that in addition to just correlating different Wilson lines together, I also have to make sure that those Wilson lines, they actually can change their transverse position, and that gives me kind of a bit different problem. And this and they move through the medium, and the medium is described now by the elastic scattering potential. And if you go to the limit of small momentum exchanges, or to small dipoles, basically small separation between these lines here, which is typically the high, what we have in the high energy limit, you get that kind of the potential looks like it's at the harmonic oscillator. So it's just the x squared. So if you look at this path integral, it basically looks like it's a path integral over a harmonic oscillator action, right? It's r dot squared plus r squared with some frequency in front, up to this additional log here. The log here, and this is again a very similar thing to what's going on in the CGC, right? In the CGC, you don't have this kinetic term here, but you have this kind of potential, or you have this kind of right. This would be the Maclaurin-Van Goppelen model, basically, in a sense, I believe. So it's almost a harmonic oscillator up to this log here. And here we see that what turns up, so what you are actually sensitive to is not kind of the full structure of the elastic scattering potential, but via the multiple scatterings, sorry, you're sensitive to this what's called Q hat, right? The jet transport coefficient. You're sensitive to the kind of second moment actually of this potential, which is very interesting. And nowadays people are looking at this, extracting this kind of how the potential in medium potential would look like in a realistic medium with lattice, for instance. So you guys are interested in lattice stuff. This has been recently studied by these guys, and I think this is also an extremely interesting direction to really what is this Q hat in the realistic medium, or what kind of X dependence is this has this potential, stuff like that. All right, so now my task is basically to resum all of these different emissions and compute the spectrum. So there are several ways to do that. So in a sense, I should just solve this path integral, and I can do that using numerical techniques. But they have traditionally, you have also many well-established techniques to deal with this. And one is, the first one is the opacity expansion. The opacity expansion is also something that Will has been working a lot on. So, but somehow here I just mentioned the first papers in this story, and it's basically taking this path integral there and taking the multiple scattering series of that path integral and just truncating it at the given order. So, for instance, if you truncate it at one scattering in the medium, then that's what's called the n equals to 1 or GLV, or and with some additional components, but it's basically the GLV spectrum, right? And when we have been studying this stuff now recently, and here we can see how this expansion works actually compared to full numerical solution. So what we have here is actually the opacity expansion up to second order, and you see, so here the mean free path is 0.06 Fermi. So if you are at the time, so now we're computing the spectrum of the gluon. So if you are at the spectrum at short times, so shorter than the mean free path, you see that the full numerical result is exactly described by the GLV approximation, by this term, by n equals to 1. However, as you go to bigger and bigger medium, so here, for instance, we're 10 times over the mean free path, you see that the spectrum starts deviating from the full solution at this gray point. And further on, this point moves to the right over here for bigger and bigger media. And this is because and this basically is due to the fact that the opacity expansion has, in fact, any expansion will have a very clear domain where the radius of convergence is smaller than infinity, basically where it converges. So the opacity expansion itself converges specifically in the hard regime. So in this tail here, that's where the opacity expansion always is valid, as you can see. You can always find an omega where the opacity expansion is valid for any medium density. But for the soft sector, the opacity expansion breaks down basically. And this is and this scale where this happens is related to this omega c basically parameter here. So it's basically given by this scale. You can have another expansion, which is this is quite new one, which I won't have time to go to the details, but you can ask me maybe later. It's called resummed opacity expansion. So instead of expanding around medium scatterings, we expand around exclusive scatterings in the sense that those are the scatterings that actually give me momentum transfer to my probe. And instead, I will resum all the virtual guys up into a Sudakov. So that simply means that I expand in one and only one scattering, or two and only two scatterings, and three and only three, etc. In a sense, and that gives me a very nice expansion in the soft regime. In the soft regime where I have very few scatterings. So I can be in a dense medium, right? But during my formation time, I only scatter with one particle. So that gives me kind of the control over the other end of the spectrum, of the soft end of the spectrum. And finally, I can do something which we call the improved opacity expansion, which obviously these names are arbitrary, but that's the way it ended up. Or you can also call it harmonic oscillator expansion, in the sense that what we expand here is around this x squared. So we are basically neglecting. We're treating the log as a perturbation. So as you remember, the potential was x squared times the log of x squared. So we're treating the log of x squared as a perturbation, and we're and treating the x squared itself as a big term. So that's just an harmonic oscillator solution. So in the end, the harmonic oscillator solution gives me kind of the behavior of dense in dense medium. It gives me a nice agreement with the spectrum in this LPM suppressed regime, right? This is where the LPM effect dominates. And the fact that I expand in hard emissions on top of the harmonic oscillator gives me also a good agreement with the tail. So all in all, we have developed kind of, built on previous expansion schemes and developed new ones so that in the end, all of these curves, at least in some regime, are covered by at least two different schemes. So basically, I can take this resummed opacity expansion and dilute limit overlaps with the opacity expansion, and the opacity expansion and the hard tail agrees with the improved opacity expansion, etc. So there is a connection between all of these three schemes in different regimes of validity. So I think I actually spent a lot of time on this. So anyway, all in all, there you have an emergent kind of picture where early on in the medium, you basically interact with the medium via single hard scattering. But as you go deeper and deeper into the medium, in order to emit a gluon with a certain soft energy, you're dominated completely by multiple soft scattering. And this is kind of a picture that emerges. And in order to show you that this actually works, we also computed the two-dimensional, so basically double differential spectrum in energy and transverse momentum of gluons. So these are medium-induced gluons with a certain omega and a certain transverse momentum. So here we keep omega fixed and we vary transverse momentum. As you can see, the spectrum is completely collinear finite, right? So it goes to zero when you take the transverse momentum to zero. But it has this characteristic peak. And we see that kind of the opacity expansion, which is used here, the improved opacity expansion somehow, compared to the numerics, captures more or less the behavior of this peak, but it's obviously not ideal. So it has both its advantages because it's lightweight. It's an analytical formula, but it also is it breaks down in cases where where it has to break down, basically, when you're away from the regions of validity of that particular expansion. So coming back again to this the space-time picture of what happens, right? So you have one parton that you shoot through the medium, and what you are interested in is what kind of quanta are going to be emitted from it. And what happens is that early in the medium, or in the phase space where you're looking at hard emissions, you are basically dominated by early or hard kicks from the medium. So you're sensitive to the kind of quasi-particle picture of the medium, while later on in this or in the soft sector, you're basically dominated by multiple interactions with the medium, and that's where you're going to pick up this kind of very interesting features where energy gets broadened out and to large angles and gets thermalized, etc., etc. So this kind of brings together both regimes, both early hard emissions that can stay inside of the jet and modify its structure, and also the large angle stuff, which basically is soft and takes away energy from the jet. So this is basically finalizing our understanding, or at least for now, the understanding of what would happen if you just shoot a parton through the medium, and what kind of response would you get, right? You would simply start creating many particles, some of them at large angles and some of them at small angles, etc. Now I should speed really up, because now my rest part of my talk is to talk about how to go to a description of full jet, right? So far, my vacuum picture is this one, but in principle, I assume that there's only one parton going through the medium. So I can think about, okay, what happens if actually all of these emissions happen late, right? So I have a very small medium, and in principle, I do something, I interact with it, and I do this, I emit something. But you can think about, well, what if I have a large medium, or I have some radiations occurring inside of the medium? What happens if I start mixing soft collinear emissions, right, from the jet together with this physics that we just discussed? So what's the difference between one emitter and n emitters, let's say? And that's related to the difference between, so here I'm showing the atlas, some preliminary plot of how charged hadrons are quenched and how jets are quenched. So typically jets are quenched much more than hadrons, or significantly more than hadrons. And that's exactly this picture between that we just looked at. For hadrons, typically you're interested in a leading parton. So you would be interested in how a leading parton loses energy. While for a jet, you would be interested in seeing how the whole ensemble of particles entering into your jet definition actually together collectively lose energy. And that's the main point of my story here. So what we discovered a long time ago is basically that there is a certain resolution effect or delay effect involved in this picture in order to compute this energy loss for jets. So the thing is that if you split into a dipole, you have one parton splits into two, then initially those two guys are going to be close in space to each other, right? And then at some finite angle, they will start moving away from each other, and at the finite distance, they will be far away from each other. So I can look at this process in somehow large NC limit, then basically I have a total color charge, which is the red thing, and at some point, when the two particles are actually split up, there is an additional color singlet dipole appearing. But that's not important. The important thing is to basically when are you able to see the difference between one color charge and two color charges? So as I said, initially this pair is in transverse space, right? It's just on top of each other at time zero. It's just time zero. It's on top of each other. But then it starts moving away linearly in time, roughly, with the proportionality constant of the opening angle, right? So the two particles starts moving away from each other. At the same time, just because I'm interacting with the medium, I'm starting to accumulate a transverse scale, which is again Q hat T, right? This is again my transverse momentum squared. My transverse, and the inverse of that is kind of the resolution size of the medium. So when does the medium, when did I accumulate enough time, enough momentum to resolve this this pair? Well, that's just given by this decoherence time here, what we call the decoherence time. So before the decoherence time, the medium just basically doesn't see two particles. It doesn't see two particles. It sees only one particle. After the decoherence time, it starts seeing both particles. And then those two particles are independent. They can just start radiating independently of each other. And in the limiting case, if I, for instance, have my decoherence time of the size of the medium, it means that I split somewhere deep inside the medium, but I propagated all the way to the end of the medium without the medium being able to resolve me, right? That gives me a minimal angle. Below that angle, the medium cannot really see anything. The medium with size L and transport coefficient Q hat cannot penetrate into that angular distance to see what's going on. And that's what's called the decoherence physics, basically. And that affects jets, because jets, explore the whole phase space. You have large angle emissions, small angle emissions, high energy emissions, short energy emissions. And in fact, some of the jets will then basically be resolved by the medium, and some of these splittings will not be resolved by the medium. So, and that's basically what's encoded in this diagram here. It's basically the phase space now, not in energy and angle, but in transverse momentum and angle. Okay, so it's basically just very analogous to the thing, but basically you have a soft and collinear divergence. So basically this phase space by one splitting is filled uniformly, right? It's just filled by alpha S radiation, the whole area here, because this is basically the log of KT and log of angle. It's basically the two divergences which I just absorbed into the logs. So what happens is that I can put a formation time on this phase space. I can just put a number on it, right? I just say that my formation time, which is omega over Q hat, omega over K perp squared, is equal to L. That gives me a line in this diagram, right? Which is this line here. So it's basically anything that happens above this line happens inside of the medium, approximately, and everything that happens below this line happens outside of the medium. So what I'm talking about is an emission, right? If an emission, I'm thinking about kind of like a Monte Carlo process. I'm going to create an emission and I'm going to throw a random number somewhere in this triangle. So if I throw a random number above this green curve, I'm inside of the medium. If I throw it below this curve, I'm kind of radiating outside of the medium. And then, in fact, due to this decoherence physics and this characteristic angle, I end up actually redefining my medium parameters a bit. Instead of just saying above this green line, I'm just saying, in fact, if I'm a bit more careful, not only do I want to be radiated inside the medium, but I also want to be resolved by the medium, then I end up in this red box, right? So here we can start discussing, what is the right physics of jet quenching? Because is it the red box, or is it the green box, or is it something else? But all in all, it boils down to basically counting how many emissions, how many times when I throw a random number, what is the kind of probability of hitting the red box compared to the full triangle? And that's it. In other words, it's proportional to the area of this red box. And so I can just do it. It's just what is it, trapezoid or whatever. I just compute the area of this red box, and that's exactly the probability, or the multiplicity, basically, or how many times if I throw a random number, I will fall into the red box rather than the full triangle. That's basically what I'm computing here. And it turns out that the probability of falling into this box grows with PT. So if I have a high PT jet, more and more emissions will happen actually deep inside the medium. And so for high PT jets, more and more emissions will happen inside the medium, so that my jet will not only be one particle, but it will be a set of particles. Okay. And then ultimately, what we want to compute, I'm getting to the end of my talk, although I never, I'm just going to show you my my results in a second, but just basically, this is the main observable that I will be interested in, the quenching of the spectrum. So I have a vacuum spectrum, which I know from PP physics, which creates me my jets. And then I assume that at some point my jets will quench and they will be interacting with the medium. And that gives me this convolution that if I know this probability distribution here to lose energy epsilon, I know how my final red, which is the nucleus or medium spectrum would look like. So basically taking the ratio of the red curve to the green curve is exactly the REA that I'm looking for. So I can do this in many ways. So basically here there are some mathematical tricks related to the steepness of the spectrum, etc., which is not important. But the point is that, yeah, so I'll skip all these details. The point is that I should just start resumming the energy loss coming from a bare quark. So I know that. And then I can start resumming the energy loss of two quarks, or a quark and a gluon, etc., etc. If I do that, I end up with what's called the resummed quenching factor. So basically, my medium spectrum is just this quenching factor times my vacuum spectrum, and it turns out that if I have just a single parton, right, then as I open the jet cone, right, I start capturing the energy that I emitted. So a single parton, will radiate energy. So if I have a small cone, a lot of energy will go out of the cone. If I open up the cone, I start capturing that energy back. So I get less and less. Quenching, which is basically this curve going up here. This is the quenching factor or the REA of a single quark, these dotted lines. But if I at the same time allow, as I open up the jet cone and increase the jet PT, I have more and more partons inside a quark. I resolve more and more gluons inside of the quark, and all of these additional gluons also contribute to the quenching of that jet. Then in fact, I end up with the solid lines. Right, I end up almost with zero net effect. Right, the fact that I'm opening up and capturing some of the energy is compensated by the fact that I'm opening up and allowing for more sources of radiation. And that's the main story of the whole thing. So basically, that's the difference between jet and parton energy loss that you just simply have to take into account. These additional degrees of freedom that can contribute to energy loss. So all in all, we managed to get a nice description. If we put in all the bells and whistles and we start doing some comparisons with data, we managed to get a very nice agreement with the Atlas data over all the centralities, just having two free parameters, where this recovery angle here is exactly this uncertainty and when do I actually capture the energy or when do I don't. And we also have a quite good cone size dependence, so you can have a narrow jet quenching and a wider jet quenching, etc., etc. In the end, we get a quite nice description of how that looks like for our jets, for kinematics. And just as a last point, what we try to estimate is where does the uncertainty come from. So as you can see, the curves here have some uncertainty bands which are related to the variation of our parameters. But we see basically that this physics related to this theta c parameter. In other words, when is the jet quenched? When is this additional gluon quenched, and when is it not? It's actually giving a huge effect to the uncertainty. So that means that we still have a lot. This is just a kind of a first try. We still have to learn a lot how, while the jet is propagating through the medium and it starts, emitting soft and collinear gluon radiation, at the same time it's interacting with the medium, the details of that bring a lot of uncertainty to our calculations. And so that's basically where we should focus a lot of our attention in the future for high PT jet quenching. So sorry for going a bit over time, but let me just summarize. We try to, together with the field, improve in all corners our description of how jets are going through the medium, how they interact, how this happens in time and space, so to speak. And in order to do that, we need to go, more and more into precision calculations. And this is really important to get predictive power in the end, because our experimental colleagues are also working hard to producing very high precision, high statistics jet data. So we are really have to push the theory to match their nice results. And what we are saying is basically still we're kind of estimating effects. We're kind of using calculations to find some simplified scenarios, or in other words, kind of this double logarithmic limit where we can do summations safely, where we can merge these pictures together. But I would say that going to higher precision also involves kind of merging really the long-standing problem of kind of describing both vacuum type cascades and kind of medium emissions at the same time, which is still an open question, but with some improvements on it, but still an open question. And so there's a lot of further avenues to explore, both in the non-perturbative regime and the perturbative regime. So hopefully we will see a lot of interesting developments also in the years to come. So thanks all of you for your attention. Thank you.
Super, that was really, really great. Thank you.
Thanks.
As usual, I have many questions, but let me throw it open to the audience if there are questions from them first.
So I have a quick question from slide 12 when you spoke about the resummation schemes. I think the first one was the opacity expansion.
Mm-hmm.
And there's that gray line at T is equals to 4 femtometers.
Mm-hmm.
You discussed this when you spoke about the improved expansions, but I'm wondering whether there's any physical interpretation to that divergence, or is that just an artifact of the expansion used?
Exactly. Yeah, here I have a slide in more detail here. So exactly what happens is, so the gray line is the opacity expansion summed up to second order, and we see this kind of the complete we lose control over this particular resummation scheme here. So this is kind of one of those examples, right, where you think you will compute the higher order and you will get a better description. So the dotted line here is the first order, right, and the full line is the first plus the second order, and it's you can think, okay, if I compute the third order, that should give me something better, because in fact over here, right, in this tail, you improved your description. So you moved your validity. So you improved your validity in the high tail, right, over here, but and you managed to extend. So n equals to 2 gives you you go deeper into omega, right? You go deeper into here, but then the behavior at small omega is completely erratic, so to speak, because you truncated. So in the sense, in this regime here, you need an all-order resummation of the opacity expansion, which is, of course, you can do that. That's what basically numerics is somehow doing, right? It's well defined if you do an all-order, but what's not well defined is a truncation, basically, at any fixed order. That's what our message is.
Okay, cool. Thank you. It's like quick follow-up question. I would have naively thought that expansions generally get better as you move up to higher order, which is not the case here. So that's quite surprising.
Yeah. So there are many examples of this, anharmonic oscillators and stuff like that. So you really have to find the point is to find the right expansion point. The point is to your expansion, as you said. I mean, if it's an all-order expansion, it's just formally equivalent of each other. They're completely equivalent. You just do formally the same thing. But at the moment of truncation, that's when the predictions will typically be completely off.
All right, cool. Thank you.
Yeah. Well, thanks for the question.
Super. Further questions? Well, why don't I jump in or follow up? And I guess in this plot that you have here, I think this is a really good place to go. I had some thoughts on this also. So when you say it's GLV, I think you mean slightly different thing than what I normally think of when I think of GLV. That I think of the energy loss calculations that are in the original GLV paper or in Magdalena's follow-up paper, and there's this very important interplay between the very hard 0th order vacuum radiation that you were speaking about, and then the subsequent evolution. And am I right in understanding that that initial vacuum radiation and the interference between that vacuum radiation and the subsequent emissions is absent in these calculations?
Yes, so the vacuum emission is, so now we're computing one emission, one gluon spectrum, and yeah, the vacuum is subtracted, yeah. So we are just focusing on the medium-induced emission. So yeah, that thing, so I think it's quite equivalent to what initially was considered by GLV and by ORS initially there, just looking at one emission spectrum. Yeah.
Okay, yeah, all right. So then that is identical, right? So if you have, this hard scattering that initially produces your hard particle, then there's some vacuum radiation and then subsequent emission, yeah, then that's the same thing.
Yeah. So yeah, the assumption here is that the momentum exchange with the medium is not so hard as to resolve your hard process. Yeah, it's just the Born level is factorized out. Yeah, if that's what you mean. Sorry, I misunderstood.
Yes, exactly. So then I was surprised. So you on the slide 12, but you don't have to go back. If I read it correctly, you took the mean free path to be 0.06 femtometers. Is that right? That seems very small.
Yeah.
So I would have expected something more like 1 femtometer, so maybe a couple of order magnitudes larger. Yeah,
it's super small. Well, but it's related to this Q hat parameter. So in other words, we can there is it's just basically just to illustrate the point. But so we took a sufficiently small time also to probe that. But yeah, I mean, depending on the choice of the parameters, you would see kind of a agreement with let's say opacity expansion equal 1, and then at some point you will just see a breakdown, and that's going to be similar in qualitatively similar to this what we see here, right? So initially it's as long as you're smaller than the mean free path, you're completely described by the perfectly described by the n equals to 1. Then as you go up in length, you start being sensitive to the second order, and then finally at some point you just collapse. Your expansion is meaningless somehow, or truncation is meaningless. Let's say not the expansion, but the truncation. Yeah.
I think Herbert wants to follow up or ask something.
Yeah. I mean, so if I look at these calculations and the way that they're set up, of course, some of these things need to be reasonably simple. I mean, you've gone quite a bit beyond the approximation we do in GymWalk, right? For the series summations to allow this thing to be to random walk in the transverse plane essentially. But other things about the geometry, right? I mean, of course, are relatively simple, right? You have one overall length scale for this thing, and so that conjures up the picture of a wall, right? I mean, essentially infinite wall in which you do something like that. Now, if you if you go back to what the hydro people have learned, right, in terms of how long to run a hydro and how to be careful about freeze-out surfaces in particular, right, and not messing up with causality because you give the freeze-out surfaces causally incorrect shapes, which I remember ages ago when I did my PhD in Uli Heinz's group, they were fighting quite a bit, right, with getting freeze-out surfaces right. Now, having a wall sit there, of course, might cause some problems. I mean, causality is a really nasty guy if you get something wrong there. Do you see any dangers? I mean, completely from the outside of.
Well, I think you have a point. I mean, our kind of right now, this is for one particular particle, so that particle will be sensitive to just one little piece of that wall, right? Yeah. But I guess when you will have many particles, they will, you could have super interesting effects from this kind of physics. But yeah, what we typically assume is that basically in this frame we just have a slab, right, which is this old brick problem or whatever it was called. But of course, if we want to have a medium expansion, then we simply have to do these kind of resumations on top of, let's say, a Q hat that is diluting, right, as the Bergen model or something like that, or some recently some also some ideas. Well, these are not recent, but old ideas from kind of thermal physics, where you get also sensitive to anisotropies and stuff like that, and you can get particular directions where you have more quenching than others, etc. Right? Some instabilities, you can trigger instability. So, yeah, I mean, this is really still a lot of different things that should be included, but this is. This is kind of sets the stage. Let's say this is again. Don't take these numbers.
You do what you need to do. What you can do first, right? In a simplest scenario as you can.
Right. Right. This is kind of our laboratory, so to speak, a simplified laboratory. But for instance, what we did for these numerical estimates of the experimental data is that we kind of sampled the realistic geometry. We sampled the hydrodynamics basically to get more realistic energy density, average energy density than what we are sensitive to. So, this is not, So comparing to experimental data, then you need to be more realistic, I think.
Is a little bit off. Yeah, no, I'm not complaining. I mean, this is just something that immediately pops into my head if I see a description of the geometry like this. Not that we would be doing any better, right?
Yeah, well, just a slab.
Yeah.
What happens if you keep these two parameters fixed and then go to RHIC?
I should have included. We have been recently looking at this with Danny and Yassine, and it does a decent job actually. So we're taking the Vishnu, I think it's the Vishnu again for the RHIC settings, and it's doing a pretty decent job. So we're pretty happy about that.
Very
luckily.
Nice. Very nice.
Finally, I think I have tried many predictions, but this one post-prediction. My predictions are usually shit.
Oh yeah, this is why it's hard. Why they pay us the big bucks.
I wish.
Yeah, exactly. One comment, sort of a final comment on that slide 12, slide I think 32 or so. I know from personal experience that going to the third order opacity is painful, but something that Ivan showed way back in the day was that the third order is really very similar to the first order. So it could be that if you did n equals 1 + 2 + 3, that things will look far less awful at smaller omega, but I can't predict how much less awful.
Yeah. I think you definitely would push your description to a smaller omega for sure, but at some point you will basically break down. I believe that has to be the case. But that's really something we have to still kind of put all the details on in our paper, but yeah. Maybe we should try it.
And then just the last question. So something that's been on my mind, and I think we may have even sort of discussed a little bit last week, was you went through and really talked in detail in a nice way how, look, in vacuum, you have this probability of emission. You say alpha S is small, but you have the phase space, and so you have to do a resummation, and that leads one to deglap. And there's been a lot of thought put into resummations even in the medium. But something that's always given me pause, even doing just GLV or BDMBS, is that there's this assumed factorization between the heart production and then the subsequent evolution. And so I wonder what you've been thinking about in terms of whether it's possible, whether it's desirable to try to have some kind of full picture of energy loss, say from prior to the nuclei colliding to then following all the way through the jet suppression. In my mind, it's very desirable, and then in principle, one would have scales that one could expand in and understand how to systematically improve the calculation. But it seems extremely daunting and possibly impossible. So I'm just curious what your thoughts are.
Yeah, I think you're right. I mean, typically, I mean, the picture we stick to is kind of remember that even parton showers, and even in that picture, you assume that there is no crosstalk between the heart cross section and the parton showers. Right? However, if you want to compute a full observable, then obviously you have also you can talk between the different. So you have two legs, right? 4 legs, 2 coming in, 2 coming out. In principle, you can have a crosstalk between any of those legs, and that's probably then we're talking about things like factorization breaking or stuff like that, right? But yeah, that's I think those effects will be super crucial if you look at large angle stuff, like we discussed last time, with Herbert also, right? The energy flow in some direction far away from jet activity, or energy flow between jets, basically. But so what we are focusing on here is basically inside of the cones, and inside of the cones is probably you're more safe from this point of view, not in the sense that there are no factorization breaking effects, but somehow your kind of description close to the beams of the jet, right, close to the fast particles, is where you could perhaps hope to have some kind of control. But yeah, I agree. I mean, in order to be able to put this into a full picture, it's really daunting, because at the same time you can ask yourself, well, when does the medium enter the game? When does the medium start, so to speak? So it's but it would be super interesting to kind of push this program to kind of more sophisticated full topology, let's say, on event or something like that. Yeah, but I have no clue yet how to go on. Yeah, it's
really interesting you bring up parton showers. So people sort of just tack on this this evolution at the end is sort of how I understand it. And that's interesting because I think in, say, proton goes to leading hadron, that has been factorized, right?
Yes. So you have exactly the collinear factorization with parton distribution functions, heart cross section, and the fragmentation function. Yeah. So we are kind of focusing on, and that is valid as long as you kind of are as long as you kind of have the leading hadron close to the leading parton, so to speak. And that's where we kind of work. Yeah.
And then
so
please go ahead.
So you can also have a similar evolution equation for jets. So you basically, instead of having a fragmentation function into a into a hadron, you basically have this. This is what Felix Ringer and this team is doing, this kind of fragmentation, or Zhongbo, right? Is having, you start out from a parton which has a cone, arbitrary big cone. Let's say there's no cone in the picture, and you end up at the jet with a specific cone. So then that's also a fragmentation function, but it's called the jet fragmentation function, or semi-inclusive jet function, or something like that. Which is what we are doing here.
So maybe there's hope.
Yeah, well, at least we for sure. What we would suggest, right, is to try to look at high PT probes and small angle jets and try to control the physics there, and then you start moving away, right? Then you start complicating your life. But just measuring something at some PT and with a huge angle or something, and claiming that you have found some specific effect, that's kind of, that's sticking your head out, so to speak. So either you're good in this kind of modeling, or but we should try to find. I mean, that's something I've been trying to promote, is to try to find a corner where you would trust your calculation, right? So really, I'm really excited about this high PT large angle jets, for instance, because that's kind of where I hope we can at least get some perturbative control, right? And then of course, there's so many regimes where that breaks down, but yeah.
Super.
Yeah.
Well, Konrad, really, thank you very much. This was
Thanks
really,
to
really
you.
great.
Thanks again also for me.
Yeah, thanks for the nice discussions.
Yeah.
Yeah, thank you.
All right, take care, everybody.
Yeah.
Cheers.
Cheers, everyone.
Cheers.
Cheers.